Everyone. So today we are going to discuss about deep flip-flop, and this is really going to be a very exciting session because I will be talking about what are the deep flip-flop and its truth table, how to draw the truth table, how to draw the timing diagram, what are the different application of deep flip-flop, and what are the different representation of deep flip-flop. So this session is really going to be interested for all the engineers as well as for the students who are preparing for the competitive examination. So there are few points which I have listed down. I will go through each points and try to make you understand. So the first point is D stand for delay or data in D flip-flop. So data means whatever the data you have at the input that is getting transferred at the output. That is why you are calling it as a data flip-flop also. And sometimes it is also referred as a delay flip-flop because whatever the data you see in the output, so that is seen at the output after one clock pulse. So that is why it is also referred as a delay flip-flop. The second point is D flip-flop will store data from input when the clock goes from 0 to 1, which means rising edge, or 1 to 0, falling edge. So this will depend on the clock circuits, okay, whether it is a positive trigger or negative trigger. So it means whatever the data you have at the input, so when the it is a positive trigger or the rising edge, so when clocks goes from 0 to 1, so you will receive the data at the output. The third point is same, it is a is trigger circuits, which I have already discussed. So this is one simple representation of a D flip-flop. You can see where I have a data in connected to D, and then I have a clock signal connected to a clock. Here the flip-flop is represented as a triangular signal. So I have written same, and Q is my output. Coming to the truth table, so when the clock is 0, okay, when the clock is 0, so whatever the data may be, whether it is 1 or 0, but the output will be Q only, Q previous. This is Q previous, okay. So that means it will be a memory state. So there will be no change in the output. It will hold the previous state. And when the clock will be 0 to 1, so it is rising, as you can see from the symbol, it is a rising edge. So whatever the data you have, if it is 0, the same will be transferred at the output. Again, when it is a rising edge, if it is 1, 1 will be transferred, okay. And if the clock is 1 and the D whatever may be, okay, so again the Q is your it will be a memory states, so there will be no change, okay. So that is the truth table. The same you can understand from the timing diagram, okay. So I have taken the same rising edge flip-flop. So this is my clock, okay, and this is my rising edge, so I will put it, and this is my data, okay. So you can see so at this point at rising edge my data is logic low, so this is my logic low, but here my data will not change, okay. It will only get updated at this rising edge. So my data will be low, and at this point at this rising edge you see the data is logic high, so I will transition from 0 to high. Again it is logic high only, and at this point next rising is my data is low, so my data will transition from 1 to 0. So this is my Q output, okay. Now let's understand how to write the characteristic equations for this D flip-flop. For this, my characteristics table, where you see the different combination of Q and D. Okay, so 0, 0, 0, 1, 1, 0, and 1, 1. So for 0, 0, my Qn plus 1 next state it is 0 only, whatever the data. For Qn 0, the D1 it will be 1. For Qn is equal to 1, D is equal to 0, it will be 0. for Qn and D11 it will be 1. So I will use Kmap. Okay, so there are, here I will write D and here I will write Qn. So this is my 0 and 1 and this is my 0 and 1. Okay, so for 0 0 it is 0, of course. For 0 and 1 it is 1. Okay, for 1 and 0 it is 0, 1 and 0 it is 0, for 1 and 1 it is 1. So Kmap, again I will group this together, and I have already explained in the previous chapter. So my Qn plus 1 will be, let's see. So for this group, okay, I am coming here, I am coming down. Okay, so my Qn is changing, so I will ignore that whatever is changing. I will go from here, so which is only D. So Qn plus 1 is D. So this is my equations, okay, for D flip-flop. Hope you have understood. Now the other point to remember is, if you see, right, there are different representation of D flip-flop. Okay, so you already saw D flip-flop with data in and clock, but sometimes the D flip-flop has also other inputs, which is preset or set and reset or clear. It means that this input preset or set will set the output to 1. Okay, and whenever there is a clear signal it will reset the outputs. It means it will be 0. Okay, sometime also D flip-flop comes with the enable signal. Okay, enable signal, it means whenever the enable is high or logic 1, then this D flip-flop is operational, so it will work as a normal D flip-flop. Whatever the data you have, you will receive in the output. But when the enable input is logic low, then the output will be hold. Okay, now there are different application of D flip-flop where we will spend some time. So the first is, it can be used to design the frequency divider circuitry, which I have taken one example, divide by 2 counter, which I will explain. It is also used for creating counter. So you can use this D flip-flop in series. Okay, use this D flip-flop in series, and then you take the output from last flip-flop to the first. So it will be, you can create a counter with this. Okay, with a D flip-flop. It can be used for developing a registers. Yeah, shift register, of course, it comes to my mind. So you can connect it, the output of one will be connected to the input of other. So in this way you can connect a, you can develop a shift register. Okay, it can be used for that data transmission also. Yeah, similar, it can be used for data transmission. Sequence generator, if you want to generate the binary sequence, okay, 1 0 0 1 1, you can use D flip-flop to generate the sequence, binary sequence. It can be used as an a memory element also. So it stores the data for predetermined time, or it holds the data, so it can be used as a memory element also. Let's see this divide by 2 counter. So where you see, right, my complement is connected as a feedback to D. So this is my clock. Okay, where you can see the rising is, and what is my, and let's suppose this is having a frequency f. Okay, now the output Q will be, you say, right, let's suppose this is 1. Okay, D, and my complement is connected to D. Okay, so when it is 1, okay, this will be 1. Okay, and this will be 0, and again 0 will be coming to D. So this is what you is saying, right, here 0 1. So if that 1 will come here, so this will be 0 and it will be coming to D, and then again this will be 0. So at the next rising is, you see this is 0. So this is how it will be, output will looks like, and the frequency will be f by 2. So this is how you can create the divide by 2 counter. You can also create divide by 4 counter. Okay, f by 4, and I request the viewer to please draw a circuit f by 4 and please comment in the section. Okay, thank you all.